Okay. Recording in progress. All right. Explain whether or not an ammeter should have a high resistance.
Sir, low resistance so that it does not.
No, sir. You can have a low one.
All right. So no. No, and because what?
Yeah, because the current listen, so it is diverged. When it diverges, it will flow to the cell. That's a different part. So the meter of the low, like facilitate that trade. Yeah, how to explain this?
Sir, like I said, so you can get the accurate reading on the meter, sir. You don't want to oppose too much of the current that's flowing through. Does that make sense?
All right, fine. I mean, it makes sense in reality. However, for our grade 1 straight A profile kind of a response, bringing in some physics into this, I'm pretty sure we can explain it a little bit more.
Sure.
Yeah.
We can say current tends to have what you call it, a thing to flow where there is less resistance, sir. So it should have low resistance so that it can get the all the current flowing through it so that it can have the accurate reading.
Well, you just gave me a full out SF for 2 little lines right there. Because the resistance is high. No. I want to know whether or not the resistance in the current should be high or not. That is what I want to know. So we're not talking about the resistance in the circuit, we're talking about the resistance in the ammeter. Think about it.
Sir,
Yeah.
I can.
Try it now.
Sir, I was saying that the resistance in the ammeter should be low because the flow, when the current is passing through the cell, I think it diverge and the flow of current that's enough. Where you go? And the flow of so basically it has to be low to facilitate the diverging of the let's say the current for go through the cell.
Hey, listen. We don't even need to huckle up yourself and talk about diverging. All right. I just know that I want my ammeter to have a low resistance so that current is able to flow through it. That's all I want to know, you know. So you going through and talking about leaving the cell and diverging and converging and doing all of that niceness. Yeah, that's lovely. All right, but you still haven't gotten to the point. The point is, I want my current to flow through, all right, especially if I want the ammeter to be telling me the current in the entire circuit. I don't want a high resistance to minimize the current. You understand? So I want it to be as unrestricted as possible. Make sense?
Yeah, man.
I hope you all saw how you overthought that a while ago.
Thank God.
Yeah. All right. Yeah, you just want it to flow freely. All right, boom. Next one. Part C. So no flow freely. So this one was from B part 2. All right, let's look at C. C part 1.
Sir, like how them said, all of them go be a 2 rooms, sir. You can just take one of them and divide it by the amount of resistance. Yeah, it's a 2 divided by 3.
Okay. All right. Let's take it in stages though. All right. And I know that it is an insult to some of your intelligence. The only reason I'm taking it in stages is you have to remember, not everybody's sharp with this electrical thing. All right. And there are some of us who still don't understand how the 3 different formula them can work. Cool. If we're talking about effective resistance, we're talking about total resistance. So that's something you need to understand first. Everybody following so far?
Yes, sir.
Yeah.
Yes, sir.
Effective resistance is total resistance. That is number 1. Secondly, what is the general formula that we use for effective resistance in a, by the way, what kind of circuit am I working with again? Series or parallel?
Parallel.
All right. So what is the formula that I use for the effective resistance in a parallel circuit?
Look over some.
Product over sum.
No, sir, that's not my general
Oh,
formula.
the 1 over the 1 over
Say the reciprocal of
1
All
over
right, so
R
1 over RT is equal to
1 over R1
1 upon R1 plus
plus 1 upon R2
1 upon R2 plus
plus 1 upon R3.
1 upon R3. I'll use 1 upon R1, 1 upon R2, 1 upon R3 because I'm working with 3 resistors. This formula right here should never ever fail you. Shouldn't. All right, if it failures, you fail yourself for this one. Cool. There are 2 other resistors that I can, there are 2 other formulae that I can use for effective resistance in a parallel circuit. However, each of those 2 other formulae have conditions. All right, so for a parallel circuit, the other one that I could use, but not for this question, is product over sum.
Yeah, that's only there are 2 resistors.
Ah, cool. So I can say, but there's an H somewhere in there. This is only for 2 resistors. So product over sum, we can't use it for this question. All right, what's the third one? And by the way, product over sum.
So technically, so you can still use that formula, sir.
But you can't use it with a one shot. You can't use it with a one shot. I know where you're going with this, Shane, because you're going to tell me that I can take 2 of those resistors and find the effective resistance of just 2 of them and then use product over sum. I hope that's what you're going to tell me, Shane.
Yeah, man, that's what I was gonna tell you.
All right, cool. We don't want to ending up on everybody's status today again. All right, by the way, this whole product over something, so it is RT is equal to R1 multiplied by R2 over R1 plus R2. And remember, we say we only use this if we're working with 2 resistors, which would be R1 and R2. So we cannot use this one. This is a wrong bang for this question because how many resistors am I working with?
3.
3, lovely. I just love that Dora vibes. All right, let's go for the third one. For the third one, what is I must do now? So RT is equal to?
So the number, one of the resistors over the number of resistors.
All right, so the value,
Yeah.
the value of one resistor over this sum, the number of resistors.
Yeah, the number of resistors.
This only apply when all resistors are the same.
Beautiful. This is only applicable
Yeah, because the resistors have a constant value. Yeah, because I see what I could have used now.
So this is only applicable if all of the resistors are the same. All right, and so it can be used for this scenario. Why? Because it said that each of my resistors have a value of 2 ohms. So here is the situation that I now have. I'm going back to this thing, and it says that each of these is 2 ohms. So there are 2 formulae that I can use to figure this out. All right, everybody say the 2 formulae?
Yes, sure.
Sir, can I scroll down a bit?
If I can scroll down, yes, I can. Like over to here?
Yes, sir. Thanks.
Yeah, man. All right, so let's run it now. So let me use this formula right here. And I can say that RT is equal to the value of each of the resistors, the value of one resistor, which is 2 ohms, divided by the number of resistors, which is what, 3? So that would be 0.67 ohms.
Yes, sir.
All right. And let's just plug it into the first formula to make sure that it's right now. All right, so I can say 1 upon RT is equal to 1 upon 2 plus 1 upon 2 plus 1 upon 2. A half plus a half is a whole, plus another half is 3 upon 2. So 1 upon, wait a minute.
Yeah, it's 3 upon 2 and then you find a reciprocal. Don't it?
Oh, yeah. All right, so 1 upon RT is equal to 3 upon 2. Therefore, RT is equal to 2 upon 3, which is 0.67. Yeah. Cool.
Yeah.
Cool.
All right. Let's run it. Next question. Oh, yes, man. Oh, wait, we're done with this.
Finish.
Oh, no, we weren't finished with this. Sorry. What's the voltage supplied by the 2-cell battery? Sorry, the voltage supplied by the 2-cell battery is 3 volts. What's the reading on the ammeter?
Yeah, we can do Ohm's law and answer to this.
All right, so we're going to use Ohm's law. Let's write down the variables that we have so we know that the voltage is what?
3.
All right, so the voltage is 3 volts, LOL for the IR. I is what?
So
I
that's
is
the
what we want to
time.
find. All right, what's the resistance?
0.6666.
0.67 ohms. So we can say, let's use Ohm's law, which says V is equal to IR, making R the subject. We have V upon I is equal to R. V is 3 volts divided by 0.67.
Yeah, I make the subject.
4.5.
I'm so sorry. What? Yeah. Duh.
So 4.48.
4.48.
So if we use the exact value you got for the resistance, did I get 4.5 exact?
Yeah, you would.
Oh, 2 decimal that.
All right, so because I rounded off and I got 0.67, that's why I got 4.48. But in reality, I would have gotten 4.5. That's right. All right. And the last part of this question now, if the ammeter is replaced by one which has a resistance of 3 ohms. What?
Or one of them or all of them?
Wait a minute.
Hold
Hold on. If the
Oh, it basically
ammeter,
say one of the resistors them now have 3 ohms. But no, whoa, hold on there.
that's not what the question is saying.
Yeah, basically say put a
take out
resistor.
ammeter and
Say,
put a resistor.
take out the ammeter and put a
Hold
resistor
on.
3
Hold
ohms.
on.
I think we know it after, sir. I think it asking for the total
Yeah.
resistance if you add an next resistor.
Yeah,
In
if you add a
series
next
where the
resistor.
ammeter was.
Yeah.
All right. So let's answer the question that they asked first, and then let's interpret what we think the question is. All right. So the question that I'm looking at says, if the ammeter is replaced by one which has a resistance of 3 ohms, calculate the new reading. Based on what so essentially what they're telling me is that the ammeter itself has a resistance, like has an internal resistance of 3 ohms. All right, that's based on what I am reading in the exam. All right, listen. So there's clearly an error right here. Cool, and I'm happy that we spot the error from early out. However, here is what I'm going to tell you. What I'm going to tell you is, when you go into your exam tomorrow morning, don't answer what you think the question should be. Answer what the question is. You understand?
Yes.
So even though this might not seem to make sense This can kind of answer. Let me explain how this can answer.
Period. I just add the 3 to the 6.0.67.
I would add it to the 0.67. If I were to answer this as how it were, if actually it can't answer. No, never mind. Scrap what I just said. The question can't answer. There's a whole other variable that's missing from this. All right, fine. Let's give the question as how it should be then. But as I say, go into CXC tomorrow and answer what they're asking you. Don't answer what you think it should be. All right, so this should now say if the
Like if the ammeter was replaced by a resistor of 3 ohms, something like that.
Sure, it's a joint output, that makes sense. You know.
if the
Seriously, what the first ammeter did measure then?
first ammeter, they never really gave a thing there.
Must be 0.
New ammeter is replaced by one which has a resistance of that calculate the new reading. Although, you know, this can make sense, you know. This can make sense. It can make sense because if the ammeter itself has a resistance of 3 ohms, then calculate the new reading of current on the ammeter.
I think that's what they meant to ask.
Which means now that if I'm going to use V is equal to IR, my voltage is 3 volts, my resistance is 0.67 ohms plus the 3 ohms from the ammeter, and I now need to figure out I. So that would be 3 volts over 3.67 ohms, which is 0.9, 0.8? 0.82?
Yes, sir.
0.82 amperes. This question is probably not wrong at all. It's just the interpretation of the question. And I can see where this can be a 3-mark question.
Sir, the 3-mark question is just for us to bust our brains. Like, I don't get it. The working out look like a 2-mark question. So why them do 3 marks?
You
Like,
get
it's
3
more-
marks for listing out your variables, writing your formula, doing the calculation, and writing the correct answer with the units. Some of you are going to go in exam tomorrow with your super smart selves because you actually are smart, but you're going to deliberately lose some marks because you're going to be skipping out steps in an attempt to just get the answer quick and fast. Do your steps, write out your stuff, write down your formula. Even if you think it's not needed, write it out. The aim of the game is that you want to rinse as many marks as possible. Why shouldn't we replace the ammeter with the 3 ohm resistor instead of adding them? The ammeter is because what you're replacing is the ammeter. So they never said replace the resistors. Because remember the setup now, no? This is the whoa, go back. This is the setup that we have. So you're still gonna have the 3 resistors in parallel, and the 3 resistors in parallel will still give you the 0.67 ohms. Right now, we're assuming that this ammeter right here, as is, has a resistance of 0 ohms. That's our assumption. So now we're getting rid of this and bringing in a brand new ammeter that now has 3 ohms. So we have to add that 3 ohms to the total resistance of the circuit and then work our way through. right, Brady, I'm gonna have to work this one over, as in later. I have to move on to the next question. All right. Yeah, cool. So we understand that last part, by the way? As in, you understand the logic behind it?
Yes, sir.
All right.
Yes, sir.
That was a no?
Yes, sir.
Okay, yes, okay. All right. Let's move to the next question. Fun. Crossdale, your favorite? Distinguish between the mode of propagation of transverse waves and longitudinal waves.
Yes, sir.
Sir, transfers.
So wait a
Longitudinal
second,
is
break down
perpendicular, right, sir?
question asking, sir.
And transverse is
Hold on.
parallel.
Hold on one second. What's that question?
That's to explain the question.
Oh, you want me to explain the question?
Yes.
How exactly does each of these waves move?
Is transverse perpendicular to its direction of propagation, and
What is
longitudinal
perpendicular?
parallel.
What is perpendicular?
Vibration.
Transverse wave, or is longitudinal? I'm not sure.
No.
Is
It's not the
perpendicular
type.
to its
Hold
direction
on.
of propagation.
Say that again.
Transverse wave is perpendicular to its direction of propagation.
No, hold on. Listen to
Oh,
what I'm
sir,
asking.
the transverse wave is one that has vibrations perpendicular to its direction of propagation.
Thank you.
Concept.
Yeah, you have to use the word vibration with your thing there, direction of propagation. So with a transverse wave, you have the vibration going up and down. Yeah, and then you have the direction of propagation going like this. So therefore, we say with the transverse wave, it is perpendicular. Couldn't bother write that out. So that's transverse wave. And with the longitudinal wave, with this one, talk to me.
The first one.
Longitudinal wave is one that has vibrations parallel to its direction of propagation.
All right, cool. So when the vibrations are parallel to the direction of propagation, that is our longitudinal wave. Have that now, Crossdale?
Yes, sir.
All right. All right, talk to me about what's that thing?
Sure, sound wave is an example.
But which one?
Longitudinal.
Longitudinal and
All
light
right, so we
wave
have,
or gamma, like any one of them for transverse.
For
all right.
heat waves.
I agree. All right, so sound waves would be an example of longitudinal wave, and for transverse wave, it would be any EM wave. It could be light, it could be gamma, it could be X-ray, it could be microwave, whatever it is.
Also, like ripples.
Okay,
But that's not.
all right. So ripples in a tank, as in from water waves.
Yes, sir.
Yeah, I'd
Sir,
rather
and the
use the EM waves though.
Sir, and the slinky as well.
And the slinky, all right. For the longitudinal.
Can you throw them?
All right, let's define these quickly.
Sure,
What's
the
the different
wavelength.
wavelengths?
Wavelength. This is a distance between the two successive crests and troughs.
Perfect.
Sir, on the, so you have to like specify and say on a transverse wave.
On a transverse wave, sure. And on a longitudinal wave, what would it be?
Like
Compressions and refractions.
Thank you. It would be the distance between two successive compressions or refractions. All right, lovely. What about frequency?
Sir, that is the number of
Sir,
complete
this is
vibrations per
period.
second.
1 second, give the young lady a chance. What was that? Who was that?
Where I was going to say what I said.
What? Come on. I want that thing there. Oh, you mean with the compression and refraction thing?
No, sir, for frequency.
Oh no, I want to hear what you say first.
Yes, sir, I was going to say the number of complete vibrations per second.
Oh, okay, cool. So frequency is the number of complete vibrations per second or the number of oscillations per second. That's frequency.
So up to my simple definition, where I say the reciprocal of the period. I could do that.
By right, that is not defining it. By right, that's giving a mathematical relationship between period and frequency. Technically. Yeah, so I'd rather you tell them that it is the amount of vibrations or oscillations per second. All right, but if desperation hit those, Shane, fine. What about amplitude?
So that are the
That is
distance
the maximum
from the
displacement of the vibration
principal
from its mean
axis to the
position.
crest.
Don't tell them nothing about no principal axis, man. On them,
Sir, I can try.
Yeah, sorry, what was that, Joel?
Sir, I said amplitude is the maximum displacement of the vibrations from its mean position.
That's exactly what it is. Maximum displacement of the wave from its mean position. And we know that the amplitude can happen on either side of our transverse wave. And yes, amplitudes do exist as well with longitudinal waves.
Instead of like using the term mean position, what other term can we use?
You can know rest position from its origin, whichever one. All right, so easy 3 marks to pick up right there. Ooh, what is this? I don't think I've ever seen this in my life. Part D part 1. Draw a wave of wavelength 6 centimeters using the axes provided in figure 1.
So when them said that means they must only draw one wave 6 centimeters.
Should I go to 12?
Mm-hmm.
So it would go to 12 because remember
Sir,
the
they
crest.
make one wavelength at 6 and then the next at 12.
All right, let's see if we can make sense of this. How you do this thing again?
Wouldn't you like start at the base and then go all the way to 6?
Several ways you can do this, you know. There's no one way.
It's supposed to be like 6 centimeters between two troughs or two crests. It's supposed to be 6 centimeters between two troughs or two crests.
Yeah. So that's why I said there's no one way of doing this. All right, let's see. We want to make sure that this wavelength thing up here is 6 centimeters. Why is this not working now?
So you can be like where it's in figure 2 below.
Yeah. Only thing that figure 2 doesn't have it at 6 centimeters.
And figure 2 is time.
Yeah, figure 2 is 4 centimeters, not 6.
So maybe half of the wavelength would have got 3. So in between the 2 and the 4.
All right, look a boy now, ramp up. Yeah, okay. All right, talk to me. What am I supposed to do?
So me just think say if we draw one wavelength length of 6 centimeters, sir.
But how am I going to draw the wavelength at 6 centimeters though, Shane? That's my question.
So you go draw start from the base, yeah, and carry it go up to the middle at 2 and the 4 and carry it back up to the middle of the 4 and the 6 and stop it.
Something like that?
Sir.
No, not like that. Sir, it would have
You're
gone
not
to the 4,
accurate.
sir.
Sir,
Yeah. Sir, start again. You start from the base, go down through the middle here, and stop right at the middle of 4. And it's no, then
Yeah.
No, but that look like
correct.
that
That
can.
I free.
But
Yeah.
that in a 2 centimeter.
That correct, man.
No,
not
because
right.
look at this now. Look at this now. Look at this now. If my starting point is at 0, my next starting point is at 6. This is very correct.
Tell them, man.
Nice.
Remember, the wavelength is a successive trough and crest.
Don't have to be successive troughs or crests. It can also be 2 identical points along your wavefront.
You so calm, dude.
So I can legitimately look for the point at which the waves start to go up and look for the next point at which the waves start to go up in the positive part of the wave and put that 6 centimeters apart. Is there anybody who not seeing it?
Sir, I was thinking of you could have just draw like a full wave and then a half wave, but yeah, that never makes sense. So
All right. you answered yourself right there. Big up yourself. All right. Figure 2 shows a displacement time graph of a. So if you stop at 6, it would be right. Yeah, you could stop at 6. They never told you how much of them to draw. You could stop at 6.
am I right?
All right, say it again. Let me decipher.
I said that maybe you could draw a full wave, so you could draw it through 2 and then go to 4 and then draw
Starting
half.
from where though? Starting from where?
From 0. You get
starting from 0.
Mm-hmm.
So I start at 0 and do. And go so?
Yeah, and then go through.
No, I'm not got it.
So how you just stop at 6?
Huh?
That's how would you stop at 6?
How would I stop at 6?
Oh, okay. Don't worry.
All right.
That's it.
Glad you did. All right. Figure 2 shows a displacement time graph of a small styrofoam cup floating in the path of water. Floating in the path of water wave in a pond. That even make no sense English-wise. Use the graph to determine the frequency of the wave.
So this is 1 divided by 8. 1 divided by 8.
1 divided by x?
Divided by 8.
1 divided by 8?
4.
1 divided by 4.
4, bro.
Yeah.
4. So remember now, you're talking about frequency is the amount of vibrations or oscillations in 1 second. In 1 second. So if you look at it, I have 1 complete wave happening in 4 seconds. Actually, it's not. Yeah, I have 1 complete wave happening in 4 seconds. Therefore, I can divide that by 4 or so.
Divide the 8 by 2.
What?
Divide the 8 by 2. Okay, so all right, fine. Yeah, you're right. I have 2 complete waves happening in 8 seconds. Therefore, 1 complete wave happen. No, but then no, sir, wait.
Sure, right, man, sir. Come just remember what period is, and period is the amount of time taken for one cycle, right? So the one cycle will be the 4 seconds.
Ah.
And also
So
frequency.
isn't the answer
is
0.25?
Yes,
Yeah.
sir.
Yeah.
Sir, because even if you do it with 8 and 2, you still get the same thing.
So if one wave is equal to 4 seconds, therefore 1 divided by 4 equal 1 second, which is 0.25. Hertz. I feel like there's an easier way of working this out though. Equal to 1 upon T. Yeah. Frequency is the time taken for one complete period is the time taken for one complete oscillation. Unanimous. Boy, I'm seeing some names here pop up in this thing. What's me? I see so much people in another something here. Who are you guys?
I just tell them in the group that it's not free.
Not true. It's all right, man.
Invitees.
Yeah. Everybody invite them, friend them. It's okay. We welcome you. Back to this now. Sorry. Frequency is 1 upon T. The time for one oscillation is 4 seconds. So that's 1 upon 4. So it's the proper working out for this. Therefore, frequency is 0.25 hertz. Yeah. Just wanted to make sure that we have the proper working out for this. Alrighty. Boy, Miss Margaret, Zoom soon run out of space. What you hanging about? Oh, you mean that somebody who changed their name to Orange, huh? Soft. Oh yeah, if there's anybody typing in the chat that's Orange, so it's not me, okay? All right, let's go.
Sir, the amplitude.
Yeah, what's the amplitude for this?
Sir, it could be 4 or minus 4.
4
Can be negative.
Just 4. Just 4.
Okay, displacement. No,
yeah. So Shane, what if this were the question that you got? So it's like this, you have 2, you have 4, you have minus 2, you have minus 4, you have 0. What if this is the waveform that you got? So I would have got like this, would have got like that, would have got like this, and like that, would have got like that. What's the amplitude of this wave?
3.
You blind?
4.
4 same way.
4.
So although it's a negative sign down there, remember now you're talking about the displacement. So you're talking about the distance between here and here. So you remember you can't get a negative distance now.
Is that true?
Yeah, so if you were to take a ruler and measure this, you're gonna get 4 same way.
So it's the largest one we use.
Yes, because remember the definition for amplitude says the maximum displacement from its equilibrium position.
Yes, sir. So that means whether negative or positive it's still before?
Yeah. So remember now, it's just like you taking a ruler. If you take a ruler to measure the distance between the midpoint and down at -4, your ruler will not tell you -4. Your ruler is going to tell you 4.
That's facts.
Yeah, right. So it's vector. It's just directional. You understand? But for this, we're measuring the magnitude of it. So yeah, it might be moving downwards, but what we're concerned with is that distance between the midpoint and the wave itself. All right, let's talk about some uses real quick.
So I think the first one on diagnostic testing.
No, it wouldn't be 1 second. No, it wouldn't be negative. Right, it wouldn't be negative any at all. If it were a vector quantity. All right, if I were to go very, very technical with this negative and positive thing, if you're talking about a change in your distance, because this right here, and if you look at it, it's really a change in your distance x from this x position to this x position. And a change in your distance will always tell you that it's a final minus an initial. Cool. It's not what you're going to be considering your final and your initial. If you're going up and down, so had this been the thing that we're looking at, your initial would be 0 and your final would be the positive number. For this one, I think it's what your initial is your initial 0 same way?
No, so initial would be
The initial is down here, so
yes, sir.
right. So it's now this negative number minus 0. Double minus positive. Or something like that. But that's not for tomorrow. We made that when we had the cake. But yeah, the answer is 4. All right. Yeah, one use of waves in the following in medical testing. What is it we use it for?
Diagnostic imaging.
Diagnostics like
X-ray.
like X-ray or
RP tester.
Ultrasound.
For thyroid.
ultrasound, stuff like that. Yes.
Cancer
Cancer treatment. Yes. Yes.
Thyroid cancer.
Oh wait, sorry. Give one example of the use of waves in each of the following. So for the medical testing, okay. All right, yeah. So testing for X-rays, thyroid cancer, whatever it is, diagnostic imaging. For industry,
so maybe cleaning, I think.
All right, fine. Ultraviolet cleaning, yes.
They're gonna use infrared.
Infrared imagery, yes.
Sonar,
perfect. Echolocation, because clearly these dolphins have jobs. Well, okay.
Of course, they have jobs, sir.
Yeah, man. The dolphins and the bats and all those other creatures with their echolocation. But yeah, sure. Industry, submarines, echolocation, radar, stuff like that. Fluorescent lighting, yes. All of these things. All right, boom. Oh, yuck. What's that? So we're done with this question. Yes, we're done with this one. Let's see if this is coming on tomorrow.
Gates.
Gates weren't in the Gates not in the
I know Gates not coming on. I'm just looking to see if any part of this is coming on.
So you better say come for it. Now better.
It can't then again, we get the art paper, so it probably comes from not
Art one himself.
Sorry, you said them do repeat questions, right?
Well, this is a specimen paper, so I mean, it just never ever ended up being in the first place.
Sir, just do the Gates in case. But it's not.
Can't put Gates for me, you know. Yeah.
What
Sir,
I'm
do it
saying?
last if that. Do the gates last if that do.
All right,
Just
fine.
do
I'll do it last. I'll do it last.
I do it tomorrow morning, sir. Do it tomorrow when you do it.
No,
Tomorrow
tomorrow
morning.
morning I play ball game. You're deaf.
Easy. Tomorrow is just calm.
Tomorrow
What?
morning.
Bro.
I don't know studying right before that not help you.
Bridget, Brenda is gonna be so confused tomorrow. Everybody just gonna be chilling tomorrow.
Except for me.
All right, let's go. Describe an experiment to compare the ranges of alpha, beta, and gamma emissions.
Sir, cloud chamber test.
Yeah.
Cloud chamber test. Okay. What else could you use for this one to compare ranges?
The foil, something.
No, not the foil one.
Not the guy got his own.
You can use something with that guy got you.
Oh, that I thought would.
I got mula.
Yeah, something with that
Gaga
GM tube.
Marston.
Sir, me don't know
No.
about that one yet,
Hold
sir.
on,
Me know
call
about
Cree,
this
call
one.
Cree,
Call,
call
call,
Cree,
call.
call Cree. Geiger Marsden experiment is a gold foil experiment. Geiger Muller tube is what we use nowadays. So we could also do the absorption test. To look at the ranges.
Sir, what about the deflection test?
Sir, what about the one we did for the lab? That one. That's the
absorption test?
Oh yeah, that one.
The absorption test.
Sir, could I use the deflection test?
To compare the ranges?
Yeah.
Sir, are the one
Not
with
really, because the deflection test now, the electric field one is looking at how an electric field affects the emissions, and the magnetic field one deals with how the magnetic field affects the emissions. You understand? So we could look at the absorption to see how far these things can travel.
Sir, would that take in the range? Wouldn't it just be the penetrative ability of the?
Yeah, because you would have tested with the specified absorber.
Yeah, but that wouldn't take in the distance. Or
Of course, you can take distance.
As in the range.
Because you can figure out the distance between Hold on.
Yes, sir, but you also have to take in consideration the penetrative ability or the different.
That's why the
emissions.
GMT is right behind the absorber.
Real.
Yeah, so I mean, yeah, I can have my source, but then I can look at thing there. I can move the GM tube and look at the spacing in between it to find out how much the radiation is affecting it without even putting the absorbers there. You understand? So I can turn this on right there, so I can be getting some big number here, but clearly, all right, watch it. $10,215. All right, we drop that back there. So let me stop that. Bring that back there. Yeah, Jaden, it's also a thing there. It's also dependent on the distance as well.
Makes sense.
Yeah. What was I sharing again? Oh, I was sharing the Instagram page on this. All right. So we can go ahead and describe either the cloud chamber test or the absorption test. I'm not even going to go into that right now. Which of these emissions would not be deflected by a strong electric or magnetic field? Gamma.
Why is that so? Why is that so?
Somebody answer him now. Oh wow, okay, wow. Nobody ain't answering it.
It said no charge in the chat.
Sir, Rani will answer.
Right. So I mean it has no
Oh,
charge.
Raman.
It has no charge. It's not being affected by, it has no mass. It's really just high energy EM waves. And so magnetism or electricity just don't affect it. That's just the nature of it. There's nothing for it to affect. Yeah. What's this now? Sodium is a beta emitter. It decays to magnesium with a half-life of 15 hours. Write down. Sorry, tiredness from yesterday just hit me. Write down a nuclear equation for the decay of sodium. All right, somebody talk to me.
Sir, sodium 24, 11, iron
Yeah, for start there.
24. So
Put the time, sir, above it.
Oh. Is a nuclear equation or anything that not enough for the time?
Sir, and then
Yeah, electron 0, -1.
All right, so I can write the electron 0, -1.
plus the magnesium 24.
Plus the magnesium. How much should I now write for this?
24, 12. 24 for the mass and
24 and 12. That's what we would write for this. Or instead of writing the electron, what could we have written?
Beta, the symbol.
The beta symbol.
It's a fancy bee.
Cool?
Yes, sir.
Cool.
Yeah, don't make them giving you half-life info right there, throw you off. You don't want a time on this arrow right here. This right here is going to be a nuclear equation. I want to sleep so badly. A sample contains 24 grams of sodium. How long would it take for 21 grams to decay?
So them ask how long will it take for it to reach?
Oh, that's crazy. Pardon me?
Them ask how long would it take to reach 3 grams?
That's exactly what they're asking.
Yes,
a question like that yesterday.
That's exactly what they're asking you.
Wait,
all right.
So this one would involve the time, no, sir?
Yeah, this one would involve the time. Do not think that you can go in the exam and you're going to say, oh, 24 grams break down to 21 grams and then try and find a fraction of something. That's not how it works. Yeah, what the question is really saying to you is that 21 grams of the sodium is now decayed. Therefore, what is left?
So you could have said 21 to 12 to 6 to...
Right. So let's go with that. So it's 24 grams to 12 grams. Because remember, it's radioactive. Half-life that we're doing, it must break down by a half. So 21 to 12 to 6 grams to 3 grams. That is where we're ending at, 3 grams. All right, so let's drop on our time for this. Each half-life is
15 hours.
15 hours.
So them ask one of them say how long would it take to decay by 87% or something?
Yeah, man. Them love ask some question there. 87 point something percent.
Yeah.
So say for that one,
I know sat the class person's got questions like that.
So why
If I'm
are
not
each
mistaken.
of them 15, sir?
Pardon me?
Why each of them 15? It would have been 45.
No.
Yeah, because half-life, the time that it took for it to move from 24 to 12 is 15 hours.
From 12 to 6:15 more.
Right. So your answer is 45 hours.
Yeah.
Sure. Is I nonsense?
Yeah, we just did I a while ago. You sound lost.
Yeah. Last
What you
one.
lost about? What you lost about?
It's a sample contains 24 grams of sodium. How long would it take for 21 grams to decay?
Right.
So where's the 21 grams? Or you know,
Exactly. 21 grams gone. It has decayed.
That's why somebody just said, and basically, I asked how long it took to reach 3 grams.
3 grams. So 21 grams, 21 grams out of your 24 grams have decayed. Therefore, you only have 3 grams left.
Then you have to show the progression to 3 grams.
There we go.
Using the half-life.
Yeah.
If it did say like I said the 24, no, the 23 grams, you that stop at 1 gram right here. So we have the 3.
Right. So the 3 would have broken down to 1.5, and the 1.5. We probably wouldn't for CSEC. We wouldn't give you.
Would I give with that?
Well, you know, for CSEC, we would not have given you to 23 grams. Would have probably told you 23 point something grams, so that even after you go past the 1, you can still divide it by half and get a solid number.
There are people asking where you get the 15 from.
Where I get the 15 hours from right here, so from part B, part 1.
So I go on the month, so I go.
All right, Zachary, what you confused about?
Sir, on this day, I think say 6 you would take my 4 marks, you know.
Yeah, but what are you confused about exactly?
21, like I get when I say the 21 out of the 24 decay already, but I thought the question would have I thought the answer would have like 21 and a half or 21 and then
no.
You like how you
So,
find like you have 24 and then 12 and then 6.
Right.
So I thought you would have started with 21.
No, I can't start with what I have left or what is decayed.
Yeah, but how long would 21 grams? How long would it take for 20? Okay. Yeah.
It's a reading. It's a reading over for me. Okay. Alrighty, I continue on. Discuss one safety measure necessary when handling a sample of sodium.
So we're PPE.
We're PPE.
Personal equipment.
First of all, me not gonna handle sodium again in my life.
Hey, is that the one?
Will reactive, sir.
Or it's in,
yeah.
Is it like in oil?
Yeah, it's in oil, but don't bring your chemistry into this. Yeah, so don't go and tell them that, you know, because sodium is highly reactive, you have to put it in oil and rate it. Don't tell them that. We want to know what precaution you're going to take from a radioactivity perspective.
Sir, keep it in a lead box.
Yeah, the box.
Keep it in a lead box. All right. Protective gear or clothing. Yeah. Right. PPE. What else? How can I handle it? What am I supposed to use?
Sir, use forceps.
All right. So use forceps or tongs. Please do not go on the people them exam and write THONGS. All right.
We don't do
not.
that, you know. You know me, we don't do that.
Right. No, there's no H in tongues.
Wait, sir, that's the wrong one.
All right.
So if we get it, we're gonna write that. Is that there?
Oh, there. All right, cool. And they said to discuss, by the way. They never just say state. So in your little discussion, tell them that you would use forceps so that you can safely handle the sodium and it would not come into contact with your skin. You can wear PPE so that whatever, just give it a little point right after, all right? Yes.
Yes,
Yes,
sir.
sir.
C. All right. Especially for the benefit of those who weren't at class yesterday. Let's look at this real quick. Oh, this is not a question we did yesterday, but we did something similar to this. Let me see if I can bring up a graph paper. Let me show you how to rope.
Sir, it's one graph question alone to get in.
Yes, sir. I mean, unless CXC wants to switch it up this year, you know.
And I feel like they will. That's the only 25 mark. Them could have. So real and true them could have done that.
All we're going. Personally, I wouldn't mind an entire paper on just graphs.
Sir, no man.
Yeah, the graph them easier.
Yeah. Uh-huh.
So thermometers.
Pardon me?
So about thermometers.
Say that one more time.
Are they gonna have about thermometers?
Or thermometers, maybe. I don't know.
Yeah, it's under
So them say temperature.
Wait, sir, have they ever given more than one like big graphs before in a past paper?
More than one big graph? They've never given more than one graph.
Oh.
It's only Cape you get 2 or 3 graphs.
What the purpose of that?
Yo, Cape, the dog them did look blank. No, I tell no lie.
Or which unit? Unit 1 or unit 2?
Unit 1.
Unit 1, them look
okay.
fresh.
Yeah, them they
You
look.
know why them look fresh?
Why?
Because them never come class.
Unit 2 was an electrical.
Oh, sir.
Why?
Excuse me, sir.
Yeah, Aaron.
I had a dream last night about like our prediction, whatever. You know, like
What's about to ask about that?
No, I never really slept last night, so.
That why?
Wow. Okay,
But
sir.
if you kind of pick up on the strategy, still, I mean, we've kind of been covering everything, you know. So,
sir.
Yeah.
Like what you say, you can hold a nap and then wake up and come back and tell us.
Okay, all right. So I must just like switch up my entire sleep pattern just to dream up the exam and come back and tell you what going.
Yup.
Yes, sir.
Yeah.
We need somebody to
Go
blame.
sleep like
Somebody to blame.
I just love the support of everybody in this class. Y'all are amazing.
Sir, you know, say tired, sir. So
Sir, you know what? You know what? Get you 30 other one them.
Y'all have no. That hope has long been gone.
That means, sir, you remember my
Wait, sir, 40.
No, sir. Everybody already.
Based on some of those SBA grades, I'll get straight ones in 4 years' time. All right, let's go.
No, that very feed.
No,
you can't them thing this year. No, you can't them thing.
All right, let's go. Y'all are ladies. Come on, let's go. What you actually seen on your screen now? What you seen on your screen?
Sir,
I realize you see the
graph.
rock. I am there showing something. I never even realized that you not seen the thing properly. All right, come, let's do this. All right, so Rihanna, this is not a CSEC, a real CSEC paper. Rihanna, a student carried out an experiment to investigate the properties of a spring. The result on the variation of length of the spring with load is shown in table 1. So we have that right there, and we have that right there. On the grid, plot the graph of length in millimeters against load in newtons. First thing, what am I putting on what axis?
Length is Y, load is
Sure,
So
load and
you
X
put length on the Y axis and load on the X axis.
All right, so length is on my Y axis and load is on my X. So this is length. L-E. This is so difficult. Length measured in millimeters.
Yeah.
And this is load.
Yes, sir.
Yes, sir.
And load is measured in newtons. All right, let's look at this. I know that my load goes all the way up to 24.
So 4 centimeters every 2. 4 every 2 centimeters.
On the X, yeah.
So Shane say I must draw what? 4 for what?
For the X
2
axis.
centimeters, the X axis.
All right, so draw 4, 8, 12, 16, 20, 24, 28, 32. So you say?
Yes, sir.
I'm pretty sure there's another way we could have done this, but okay, fine. Let's take it for now. And for this, all right, you know what? Best practice is perhaps I should read through the question before I actually go ahead and plot. I want to plot that. I have that to figure out. That's use your graph to determine spring's length. That's a y-intercept. What mass must be placed on the spring to produce an extension of 9 minutes? This is the question we did yesterday.
Yeah,
Sir,
you said that. Sir, you said that.
I know, but we never talked about Rihanna yesterday. Who's that girl?
What? The precautions.
No,
we skip that.
No,
we skip that.
Yeah, all right. Come. Let's do this real quick. Like how we did this yesterday. So we want this to go up to, and it's a very different value of length as well. The length you come. Yesterday length did go all the way up to like some big numbers. All right, so 2.
2 for 1.
Can I go 2? 2, 4, 6, 8, 10, 12, 14, 16. Yes, I can. All right, so that is 2. 4. Who are these people? 2, 4, 6. I feel like curving. 10, 12, 14, 16. I can't. Yes, I can. 18. No, I can't. Guys, I really remember sit down and do this.
I'm gonna tell you, say
So wait,
1 to 2.
5 did use yesterday.
A 5 they use, but that went up to 36. So
You count with 5, so I'm saying always 5 are the correct for me. So.
All right, fine. 5, 10. This might be too small. 15, 20, 25. Way too small.
Yesterday, so
There is 4.
Sir, you wanna say
again.
1 centimeter equal 2. How much time tell you? Sir, wild.
Can I go
Yes,
back?
sir. Use 4.
Sir, use 1, sir.
Corey, shut up.
You want a conky?
Oh, that's Shane Curry, guys. By the way.
All right, so you say use 4?
Yeah. 2 is called 4. It's not hard.
All right, fine. 4, 8, 12, 16, 20. 24.
Sir, use 3.
Yo. 28, 32.
That did for a long time.
Yeah, only thing that I am kind of dunce, so I can't read this off. Anyway, you're going to do the reading off for me. So cool. Let's plot this real quick.
Third come, each centimeter or look a bit is 0.4 for the Y.
As long as you can tell me what is what to me. All right, let's run it. So for the 4, I need to find 18.4. So that is 16. Where is it? 1, 2, 3, 4, make it 17. 1, 2, 3, 4. No. How much is thing there?
So 1 box is 0.4.
Yeah, that's how it is.
No, but then why would we even do that? That's so stupid. All right, one box is 0.4. I deserve a box. 16. So this is 16.4, 16.8, 17.2.
Sir, the one at the middle are 16 and 20 are 18.
6. This one right here is what, 18?
I can't see where you're pointing.
As in, this is 18?
Yeah.
Mm-hmm. So that's 18. So doing 18.4?
Yeah.
All right,
So
18.4.
that was
Let's put
first
that.
line, sir. First line of the 18.
So next, 20.5. Next, 22.4. This is 22. Next, 24.3. It's my estimations for me. 26.4. And 28.5. Look somewhat decent.
Yes, sir.
Right. I mean, they're probably incorrect. But
So this one do have no little curve in it?
No, no curve.
No, kind of go up to 32 like yesterday on 36.
Yeah. This student was calm with the experiment. All right, let's run this. So I want a line of best fit for this.
Sir, you know, so we'll get something like this on the wait. No worries.
I wasn't worried.
You said the graph can cover any topic, right?
Sure. All right, that kind of look like a line of best fit right there.
Yeah, kind of.
Yeah, it looks best fit-ish. Fit-ish. Let's not say that again. All right.
So the answer for me is 16.
The answer for you is 16. Yeah, it looking like 16. It's just at the point right here is a little bit off. So I know that my y-intercept is 16. All right, cool. We need to figure out the slope of this graph. So perhaps I can use anybody find any nice points for this one?
So 28 on the load.
Huh?
28 on the load.
28 on the load. And but 28 on the load would give me what on the thing there? That would be what, 30 point, about 30.6.
Sir.
Mm-hmm.
So isn't 28 on load past what the table gives us?
You can use any points on the line of best fit. You don't have to stick within the limit of that.
I like 30.4.
Hmm?
28 on the load like 30.4 on the length.
30.4
or 5
is all right. Yeah, it will be like 30.5. Quite go above the little box. All right, so you say I should choose this point right here then? Choose this. And for what it's worth, I mean, I can always go ahead and choose 16 and 0. Yes, David?
Never mind, so it's fine.
You sure?
Yes, sir.
All right.
There would probably be a better point But since he's in that one.
All right, so so I'm going to use my y2 minus y1 upon x2 minus x1 is equal to slope, which is called p. I said that I'm using what and what now? This is 30.5. That's all we said?
Yes, sir. I'm doing it.
30.5 minus 16 over 28
Over 28 minus
0 equal p. Therefore, p is equal to, I don't have a calculator. Somebody do this for me, please.
It'll be
0.5.
How much? 0.5?
Yes, sir.
So 0.52 if I do decimal place.
Tell me if it's 2 dp. It's 1 dp.
Sir, 1 dp.
1 dp.
All right, so that's 0.5. What are my units?
Newton meter.
millimeter.
Newton.
Nope. Thank you. Go again, Birds.
Newton millimeter.
Millimeters per Newton.
Where's the bird? Where's the bird?
I thought I heard Birds. I'm so sorry. Remember that I'm plotting length on my y-axis and load on my x. So it's millimeter per Newton. Cool?
Yes. Is the next one.
All right, next one now.
1 over 0.5.
Sir, 2.
Sir, this one is 2 Newton per millimeter.
2 Newton meter. 2 Newton meter.
Hold on 1 second. Where are these people? Sorry. All right, so what I must do now? We're doing part C now.
Sir, 1 over 0.5. 0.5.
All right, so part C. Given that the spring constant, so K is equal to 1 upon P. K is equal to 1 upon 0.5 millimeter per Newton. Therefore, K is equal to 2.0 Newton per millimeter. Part D.
Sir, 16.
Previous.
16 millimeter.
All right, so part D, at x equals 0, y is equal to 16 millimeters. What mass must be placed on the spring to produce an extension of 9 millimeters?
Can you use the hooks formula? I have the spring constant and the extension.
There are 7 marks for 1 question.
Let's see now. F is equal to kx. So F is equal to K, which is 2.
Yeah.
Multiplied by 9 millimeters. So the force is equal to 80 newtons, but it's not force that them asking me for. What are they asking me for?
Weight, mass times gravity.
The mass.
Mass times gravity.
So if weight is equal to mass times gravity, mass is equal to weight divided by gravity, which is 80 newtons divided by 10 Newton per kilogram.
1.8.
Which is equal to 1.8
kg.
kilograms. Yeah, still don't see why it would be 7 marks.
7 marks.
But you know. But I'm happy. I can see that we're learning. I mean, breeze through this.
Question,
Stage,
sir.
pardon me? Yeah.
So why didn't we use the gradient value for the constant?
Because the gradient is 1 upon the spring constant.
So it's the inverse.
The gradient is a reciprocal of it. So see there, part C says that given that the spring constant is equal to 1 upon P.
Oh, okay, so yes.
All right, cool. All right, stage 3 precautions that Rihanna would have taken to ensure the accuracy of the readings and to prevent damage to the spring.
When she
High level
extend the
readings to
spring,
prevent
yeah,
parallax
high level.
error.
All right, so high level readings to minimize parallax error. That's one.
For ensuring you don't exceed the elastic limit of the spring.
Ensuring that you don't exceed the elastic limit of the spring. All right. How's she gonna do that?
Or by removing the mass after you get the measurement.
Okay, cool. Thirdly,
Record before you add nothing to smart that up.
yes.
So
We
ensure the
read.
spring is resting against anything.
Say that again, Miss Reese.
Ensure the spring is resting against anything.
Right. So I want to ensure that the spring isn't resting against anything, that it is that it has free oscillation, yes. Why all of these answers sound oddly familiar, man?
Why, thank God for Saturday, I wouldn't know nothing.
Why?
Sir, measure the initial spring's length.
Shane, all right?
Sir,
So
yeah.
measure the
So
original length of the spring.
Go again?
Take multiple measurements and find the average.
We can take multiple measurements and find the average. Yes, we can. All right. So we're done with this question. Let's see
So
what
you're
we can take.
posting, sir.
Mm-hmm.
So you're posting this record same time?
Where should I post it? Where do you want me to
In
post
the
it?
classroom.
No, not everybody here know about this classroom thing. Where do you want me to post it?
So I suppose it's somewhere everybody can see.
Post it somewhere that everybody else can see it.
Yeah, but I don't know which part that.
So you know what YouTube channel or something?
I just can like send the link and we share the link. We do not get it.
Why are you calling me out, man? All right. I'll upload it to thing there. I'll upload it to YouTube. I'll tell you what the YouTube thing is after. But I drop it on the IG live, you know? I mean, on the IG. That video something there. But it's all right. It's too much work.
Yeah, there's a regional man in the chat.
Pardon me?
There's a regional man in the chat.
Who that?
Regional in physics.
Regional in physics. All right. I died.
After the compete, no man, Jano star.
Yeah, man. Typical laptop computer operates on a 18 VDC, 18 volts DC. As a result, to safely power a laptop, who writes laptop like this? From 120 volts AC, domestic mains, a specialized cable must be used. State 2 essential components that must be included in this specialized cable. I feel like they don't want to say cable. I feel like what they should have said is a specialized adapter. That would make way more sense. But okay, what do you think would be in this specialized cable or adapter?
Sir,
Go again?
sir, I feel like a transformer.
I'm feeling a transformer as well, you know. Like a small transformer would be in the adapter.
Sir,
Anybody else? Yeah.
you remember that? I don't know if it's you. Like You said we did a question with like something like a volt protector or something like that, or I don't remember if you.
Well, if it named volt protector, it's not me. Two essential components. Wow.
Circuits are earth wire.
A earth wire, yeah. That's on essential to me as well.
So, sir, the transformer and the earth wire?
I think it can work. I honestly think it can work. I hope you all hearing the doubt in my voice right now. I should have probably stopped the recording before this. But okay, fine. Let's run with that. Sketch two separate graphs to show the variation of voltage versus time of a 120, not true, of a 120 volt AC domestic mains and the output of a specialized power cable. Assume that the power cable is only able to accomplish half-wave rectification. All right. So,
Sir.
Contextual clues, guys. What device allows for half-wave rectification?
Diode.
There we go.
Sir, that me just said I go saying, sir.
4i.
Huh?
4i.
Yeah.
Yeah, what's the answer, sir?
You could have put a little transformer, you could have put a diode, you could put earthen wire.
Sir, I that me
no,
supposed to say voltage regulator.
There we go. Okay. Woo. Getting somewhere. All right. So what's we're doing for this now? So this is 4A part 1. So it's a diode, transformer, earthen wire. You seen the whiteboard, by the way, right?
Yes, sir.
All right, cool. Part 2, we're sketching some stuff. So for part 2, we want to show the first one, which is what? Voltage versus time of a 120V AC domestic mains, not a problem. If it's AC, what will the waveform look like?
Up and down.
All right, up and down. Yeah, man, sounds very physicsy.
Yeah, man.
Cool, so it's gonna be a sine wave. All right, and we want it to peak out at what value?
120.
120, thank you. It's important that you put a value on this down here. We don't care about what the values of the time. Well, we can put time in seconds. We can put volts in volts. But we can put some values on our y-axis because it told us that's a 120 volt AC. Make sense?
Mm-hmm.
What would the second waveform look like though?
Half wave.
So for all right, so hold on, we just need to make sure that we know what the half wave look like. By the way, what values would we use for this one now?
60.
No. Half wave don't mean half of the voltage.
Sir, wouldn't you have this?
60.
Read the question. Go again. What was that, Vanessa?
I was asking if it wouldn't be the same 120.
No.
Sir,
if it's a specialized power cable, read part A again. Read 4A.
Sir, I just say 18.
18. Thank you. What must I do with this half wave now?
Up and down on one side, like the top part. Like you just
do it like this?
No, sir.
Absolute rubbish. That's right.
No, like space between them.
All right. Thank you.
You never let me finish.
So, all right, I'll put time over here in seconds. Sounds good? Look good?
Yes, sir.
All right, cool. An electric kettle is connected to an alarm that sounds whenever the kettle is switched on and the lid is left open or the water level is below the heating element. Oh my God. There's so much thinking. Figure 3. Hey. Figure 3 shows the circuit that controls the electric kettle's alarm. What are the points L, M, and N collectively called?
Sorry, input.
Thank you. Part 2. At CXE just giving away marks. What logic gates should be placed at A, B, and C? Oh, that's crazy. Why would they ask you that? Hold on, let me see something. Come through CXE with the contextual clues. All right, watch out now. You have L, M, and N. So let's look at LM and look at the output X. LM with the output X. I can come back over here and look at this. Oh crap, there's no output X. Where's N? Oh, N is right there. Oh man. They never give the output.
The wicked still got.
Sir, I think they're expecting us to like analyze the whole thing.
Yeah, but for 3 marks though.
Yo, that not working.
Wow, watch it. All right, we can do this. So the alarm will sound whenever the kettle is switched on and the lid is left open. Oh.
Oh, so you could have put the AND gate at A, you know.
All right. They gave you the answer. Just have to read. Part B listed it out. English is a lovely thing, you know. The electric kettle is connected to an alarm that sounds whenever the kettle is switched on and the lid is left open or the water level is below the heating element.
Sir.
So we want a OR gate at C.
Yes, sir.
Yeah.
Right, so let's go. We have a A, we have a B, and we have C. We want an OR gate at C. Why is it that we want an OR gate? Because we want it to think there. We want it to sound if the lid is left open or if the sensor is too low. Something like that, right?
Yeah.
All right, what gate would we want at A? And what gate would we want at B?
Yeah, I was saying probably an AND gate at A, I don't know.
All right, so we want an AND gate at A, meaning we want power to be going at the kettle. So we know that both A and B are getting, once it's an input state of 1, that means power going to the kettle. The kettle is on, right? So if the kettle is on and the lid is open, then it will give a signal, right? So A should be an AND gate. And if the kettle is on and the water level is below the heating element, then it should give a signal as well. So B should also be
AND gate.
an AND gate.
Sir.
Yeah.
What is the point of the table on the next page?
Well, I don't read it yet. I was hoping that it could have given me a clue, but okay, let's read it. The table below shows the input for a truth table. In the space provided for your answers, complete what space provided? Complete the truth table to show outputs at X, Y, and Z that satisfies the condition that will make the alarm sound.
Sir, wouldn't it be better if they gave us this part before the whole gate?
Well, I mean, it wouldn't matter though, because these are just all inputs. Remember now, I was hoping to look for output to see what the gate would have been. So no, it don't matter. All right, let's put this table over on the whiteboard. And let us see if we can figure out life. All right, so this table is here. Alrighty, so we'll go with this. And what I want to do, we want to put a X, Y, and Z on this. Man, them couldn't even make the space on the table. Height of laziness. Could have done that better. All right, let's run this. Therefore, I can go back and look at this. And we said that we're using A as an AND gate, B as an AND gate, and C as an OR gate. Right?
Yes, sir.
Yeah. Yes, sir.
All right, so L and M is going through an AND gate to give X. Ready. 0 and 0.
0.
Yeah.
0 and 0.
0.
0.
0 and 1.
0.
0.
0.
0 and 1.
0.
1 and 0.
1.
0.
1
0.
and 0.
0.
1 and 1.
1.
1.
1 and 1.
1.
All right. Why? For Y, we want to make sure that we have a 1 and a 1. So everything looks like it will be, sorry, a 1 and a 1 for M and N. All right, so this looks like 0, 0, 0, 1, 0, 0, 0, 1. Everybody see that?
Yeah, man.
Z use what? Y?
And for Z now,
Sir, M and N, you do for Y?
yeah.
Alright.
X and Y for Z.
For Z now, we're looking at X and Y. And remember that C is an OR gate.
Yeah.
Cool. So once we have a 1, we're going to get an input state of 1. I mean, an output state of 1. So that's 0, 0, 0, 1, 0, 0, 1, 1.
I find it so hard to go study logic gates right now.
You're not studying it.
What do you think of me, one?
Just remember, I'm really just working this through. I honestly don't think logic gates is coming on your exam tomorrow, but we see what
unexpected.
There we go. You understand? Hold on, Calcree. What is this?
So this is
that would
input.
just do.
LOL. LOL.
That's crazy.
Oh, because remember to them gave the space to work it out.
In the space provided. They gave the space provided. Okay.
Oh.
Okay. All right. Write your answer to question 4 here. What's question 4? Oh, we do all of that already.
We do all of that already, sir.
So we're done. Oh no, we're not done. This last one. Discuss one way in which laptop computers have evolved into a versatile tool of communication. How is this even a physics question?
So that's a common sense
question.
So probably CSE just didn't want to give Elko 2 marks, because you know probably people they're gonna feel them time.
Funny if you don't get the 2 marks from this though.
And I would IT means you actually know the answer to this, you know.
What the man them say, foreshadowing for IT. All right. Discuss one way in which, yeah, all right, fine. Yeah, tell me now. One way in which laptop computers have evolved into a versatile tool of communication.
I don't know, nigga. Say upgraded processors. I don't know.
Upgraded processors. What does that have to do with communication? You thinking too hard?
Sir, we use it for Zoom class.
We use this for Zoom class, yeah, man. Johnny, this question was CXC made this question back in 2012. There was no Zoom.
Sir,
Yeah.
Sir, can interact with the teacher then?
Can interact with your teacher them? Oh.
Bruh.
Instead of like written letters.
All right, listen.
Hey,
Wait a second.
it has
Okay.
signal.
Okay, so instead of using written letters or like a pigeon with a string and a message, laptop computers can now connect to the internet that can facilitate the transmission and the receiving of various types of communication.
Webcam.
Whether it's email, instant messaging, video calls, whatever it is.
Yeah.
You can make that up. Just use sense with it. All right. Yeah.
I was just a guess, but I was saying you could have like you said radio waves of being able to transmit through air because what you just said a while ago.
If you're going to go that route though, Antoine, if you're going to go that route, then you're going to have to state how the laptop computer itself facilitates the transfer of data over these radio waves. Right, so you're gonna have to state that there is some kind of internal antenna inside of the laptop that allows for the receiving of the waves and the transmission of the waves.
That about signals, you know.
All right, so let me end the recording right here because we did cover the entire paper.